Hey guys, you're watching Python tutorial videos on my YouTube channel, Python for Microscopists. When you get into machine learning, you probably hear a lot of terms like supervised, unsupervised, regression, classification. So a few of these terms that are thrown out there, and you probably know what these are. If so, please skip this tutorial. The goal of this tutorial is to provide a quick introduction to what regression is, what multi-class and binary class and multi-label challenges are in machine learning. And in the next 3 to 4 videos, I'm going to show you an example for each of these using Keras and TensorFlow. So this is just a introduction or a background video for the upcoming videos, let's say, okay? A preamble to the upcoming videos on these 3 or 4 specific topics. This hopefully will make sure that all of us are on the same page when we talk about, especially I was confused for sure between multi-class and multi-label. For a while, initially, I didn't know the difference. So let's provide some context here. So starting with, first of all, I like this picture. I was Google searching for a comprehensive view of machine learning, and this one summarizes it very well. I don't know who the original author is. I got this from this Oracle blocks, but I saw like at least 5-6 different variations of this, so probably someone copied from someone else. But anyway, I directly got this from Google search. So at the machine learning, the 3 main branches of machine learning are unsupervised, supervised, and reinforcement learning. There are a few other variations, but primarily these are the type of algorithms that we deal with, or the type of problems that we deal with. Now, unsupervised learning is you have a bunch of data, but you're not telling the system what the labels are, meaning there is a bunch of data, you figure it out. So this is a typical approach would be clustering, right? If you have k-means clustering, all you're saying is, hey, I have all of this data, find 3 clusters within this data, meaning it eventually finds these 3 hopefully well separated clusters, and then when you look at the data you'll get an idea, oh, this one's telling me that okay, this is the label, this one's telling me this something else is the label, or whatever. So unsupervised clustering is one of the primary techniques. Dimensionality reduction is another, and let's not get into this, like principal component analysis, for example, falls into this unsupervised learning, because you just have data and then let it figure it out what type of labels are present. Now, reinforcement learning is, again, let's not spend too much time talking about it, but what it is it's rewards some type of behavior. Okay, so this is reinforcement. It reinforces certain type of behavior, meaning it learns from your behavior, and it actually reinforces that type of behavior or rewards that type of behavior. Now, supervised learning is where we will spend some time, because this is our classic machine learning, at least from the microscopy point of view, or even for any image analysis point of view. Now, supervised learning again has like 2 groups. One is classification, one is regression. Okay, and we'll talk about what these are in a minute. So regression, just to be quick, like first of all, supervised learning means you're providing data and you're also telling what the result is. Okay, so if you're looking at NFL, for example, football, okay, you say, okay, this is the team statistics, and this year the team won Super Bowl, or the team went into the playoffs or something. So you give like what the end result is. So when you calculate, you can calculate the probability for the upcoming season given certain statistics. Okay, so I'm just using sports analogy, hoping that we all can relate to it. And my friends from India, you can think of this as a cricket match where you have, okay, with these players, with these type of statistics, we have won so many matches. And if this type of team is put together, and we play against, I don't know, Australia or some other team, what are the chances of us winning, right? Now, in this case, again, you can either divide that into a classification problem, which is, are we going to win or are we going to lose, right? This is a classification problem. If you want a regression problem, then it is like, okay, if we play, I don't know, Australia or Sri Lanka or whatever the team is, how much score are we going to do? Like, is it, then you'll come up with a range, right? I mean, you basically, okay, if you play against Australia, it would be with 90% probability, we can say that, okay, the score would be above 250 or something, or you can predict exact score. So that's the regression type of problem. So this is the heart of machine learning. Now, just have a quick look at regression. Regression is anytime you have regression, again, you have a data and you're fitting it to this some sort of a data, and the classification is you're separating the data into two different classes, as the name suggests. Okay, so in regression, we are predicting a numerical value. What is the score going to be of a specific game or a match? And here we are predicting categorical values, right? Is this going to be a win or a lose? And then we predict a categorical value for that, right? Win is 1, lose is 0. So that's what categorical means. Now, what type of algorithms exist for regression? There's a whole bunch. Like linear regression is probably something that you're used to. Support vector machines can kind of fall into both regression and classification, same as random forest. Some of these have some overlap. Now, if you look at classification, very similar. You have logistic regression that can be used for classification. Convolutional neural nets can also be used both for regression and classification. Again, look at the optimizers and all that stuff. We'll get into that. Now, classification, like further, if you look into it, there are many classification styles, right? There is binary classification, there is multi-class, multi-label, semantic. So you hear a lot of these terminology. So classification itself can be a bit deep in terms of the science itself. Now, I'll provide a quick overview of the three types of classification here: binary, multi-class, and multi-label. And from the name, this should be pretty straightforward, pretty obvious. Binary is, let's look at this, these two images. The one on the top is infected cell, and the bottom one is not infected. Okay, so this is a binary classification, in which case the output is going to be only one value. Okay, that one value, if that value equals to 1 or close to 1, that means it's closer to one of these. If it's equal to or close to 0, that means it's equal to something else. In this specific example, if I say my value of 1 is not infected, that means my value of 0 is close to infected. So it is binary. Is it either infected or not infected? Okay, is this a cat or a dog? That's it. It can be either this or that. Binary classification. Okay, and for that, again, we'll get into, when I talk about binary classification, we can see what type of optimizer would be ideal and all that stuff. Now, multi-class, as the name suggests, it can be one of multiple classes. Here it can be one of two classes: infected, not infected. Here, multiple classes. I took an image of mitochondria. Now, if you're trying to classify this image, again, we are talking about classification of an image, okay? Classification of this image, because it has some of these going on. This is infected, that's not infected. In this case, this is mitochondria. So it could be any of these organelles that's part of a cell, right? I mean, that's what I'm defining my problem as. This could be a nucleus, a mitochondria, a ribosome, lipids, or something else. But my output is going to say that this is mitochondria. Well, if my algorithm, if my training is good enough, it's going to say this is classified as mitochondria. That means only one true answer, all others nothing. Okay, so this is multi-class classification. Again, this name sounds weird. We call it multi-class, but still only one thing is classified here. Okay, so this is almost like binary, except think of for each of this as, is it nucleus or not nucleus? Well, this is definitely not nucleus. Is this mitochondria or non-mitochondria? This is mitochondria. So the value for mitochondria is 1. So once mitochondria is taken, it cannot be anything else. So this is mutually exclusive, meaning it can be only one of this. Multi-label is exactly opposite of this. So if you have an image of the entire cell, now I see a whole bunch of mitochondria here, right? So there are a whole bunch of mitochondria. So if you ask that, okay, do I have mitochondria in this image? Then you classify this. If you have 1,000 images, and this is one of the images, and you say, okay, classify this image, then I classify this as an image that contains mitochondria, that contains nucleus, a bunch of lipids. You see the dark dots, and then lysosomes, which are probably these bright spots, and there's a whole bunch of ribosomes, but you can also classify that. So this image falls into multiple classification. If that sounds a bit confusing to you, for example, the example I'm going to use for multi-label classification later on is going to be, for example, movies. You have a bunch of movies, and then how do you classify a movie like Titanic, for example? Is it action? Is it adventure? Is it romance? Is it a documentary? I mean, what classification is this? In that case, then each of these class has a probability. Okay, is this action? Well, maybe low probability. Is it adventure? Maybe slightly higher probability. Is it romance? Probably higher probability, right? Is this some sort of a documentary? I hope you guys don't think that Titanic story is real from the movie. So that's definitely not a documentary. So the probability should be very low, okay, for that movie. So you can have multiple labels, except each label has a probability, and those probabilities don't need to add up to 1. It can just be that, okay, this is 80% a romance movie, and it has 60% of action in it, and so on. Okay, so this is multi-binary, multi-class, multi-label, and in fact, real-life challenges can be very complex. It's not just one of these, right? I mean, it's not just one of these. It could be a combination of this. So I just am putting, like, here is the reference of one of the images I found during my Google searches. In fact, I have to dig a bit deep into this paper because I happen to love the abstract and a little bit of what I read. So anyway, here is the title. What these guys are trying to do is, as you can see, this is an HND stained image, histopathology type of application, and apparently they are trying to label each of these nuclei by doing instance segmentation, right? So if you look at this top one, this is semantic segmentation, meaning background versus nuclei. That is semantic segmentation, where every pixel that's a nuclei is colored in red. Every pixel that's background is colored in blue. Okay, so when you do a pixel level segmentation, it's semantic segmentation. Obviously, in this case, it's a binary semantic segmentation, meaning every pixel can be either a nuclei or a background. Okay, so that's what you see over there. Down here, you see that, okay, this is now they are separating them into different types of nuclei. Looks like they have different shapes here, different shape here and there, right? So they're now separating different types of nuclei. So this is almost like multi-class problem right here, where you have I mean, at a given nuclei it's multi-class, but then it's multi-label. You see how you have one type of label here, second, third, and fourth different types. Now they are doing some magic to actually, some type of learning to get this instance segmentation. Again, instance segmentation is like semantic segmentation, except here each nuclei is well separated. It's not actually using watershed or some traditional method of separating. This is actually separating each instance of this cell. Again, if you have 10 people in a photo, okay, you can say that these are all people, but then you know that these are individuals, right? So that's what instance segmentation is here. And now they're combining this nuclear type prediction plus instance segmentation to get a beautiful, more importantly, a useful image at the end. So these can be real life scenarios. I'm not going to talk about this again. Here is the paper. You can go ahead and read their paper, but I hope to provide you a good background about what we are talking about when it comes to binary and multi-class and so on. So please stay tuned for the upcoming videos, because I'm going to show at least 3 or 4 different types of examples, one for regression, one for binary classification, one multi-class, and one multi-label classification. And of course, I'll provide the code as usual on my GitHub page. So go ahead and grab it and try to learn more from those, from practically working with the code. So anyway, no coding in this tutorial, great. But in the next one, we are going to jump into some code. So thank you very much for your patience. And again, as usual, I request you to please subscribe to my channel, and it keeps me very encouraged in creating more such videos. Thank you very much.